Hello, this lecture is about reduced row echelon form. This is one systematic way of finding of calculating really the solution set of linear systems of equations. So we're gonna briefly go over representing systems in this matrix vector notation. So a matrix will be an array of numbers. Here, in general, these numbers are going to be considered as being elements of the complex plane, as being complex numbers. And a matrix is also in general form is considered a rectangle. This array of numbers contains rows of numbers, and it also contains columns. Therefore, entries of the matrix are commonly referred with two subindices, one referring to the row number, another one referring to the column numbers. And so here's a brief example. This matrix has 3 rows and it has 4 columns. And here's entry in row 2, column 3, written as B sub 2, comma 3, and that entry equals -6, and so on. Okay, so what we want to do is to take a linear system and represent the linear system in terms of this new notation. So another particular case of matrices are going to be those forming the columns of the matrix. These are like vertical arrays of numbers. And a column vector, this is going to be a vector, is here denoted as V, and entries for a vector you only need to specify one location at a time. So V sub I denotes the ith entry on that list. Here's the vector of zeros. So going into the type of general notation, this denotes general system that contains m equations. Okay, so a system this system has m equations and it contains n variables. Okay, so this has n variables. So the matrix representing the coefficients, each coefficient is multiplying a variable. This matrix is going to be a matrix that has m rows. Okay, so it has as many rows as equations, and it also has n columns. So it has the number of columns of this matrix matches the number of variables in the linear system. So that the matrix of coefficients has m rows and columns, and the vector that stores the values on the right side of the equations, here's a vector that would be that vector has as many entries as equations. So this vector is going to have m entries, m elements. And the variables which are stored in the vector denoted here by x, these variables x1, x2, x3, this another way of calling the variable is the solution vector, right? So if we find values for each of those x entries, then those values will be a solution of the system of linear equations. Compact, short way of writing linear equation, a system of linear equations, is by using this letter ls, right? So this denotes here linear, L is for linear, and S is for system. Okay. And so this is one way of writing, referring that we're referring to a linear system with matrix of coefficients A and the vector of constants on the right side of the equations B. So here's an example. We have 3 equations, 5 variables. So we can collect the entries of the matrix of coefficients. Here you can clearly see how, for example, the second row has a 0. So that means that one of these equations is missing a variable, and precisely is because here we have an equation 2, 3x1, 1x2, you can write 0x3 and plus 1x4 minus 3x5. Okay, so from these three equations with 5 variables, we can write down the matrix of coefficients, and then the vector of constants is collecting the terms that are on the right side of the equal sign. So this vector contains 9, 0, and minus 3. So now that we have a representation for a linear system in terms of the matrix of coefficients and the vector of constants, we're going to do something. We're going to define a new matrix that is called the augmented matrix. So the idea is that this system looks something like this. The original system looks like, here's the matrix of coefficients. In general, it is assumed this matrix is rectangular, and that multiplies vector storing the variables, and then this equals another vector. This is the vector we call b. So here on the right side is the vector b, and this matrix here is A, and this vector is a vector B here, represented as a vertical list of numbers. Okay, so now what happens if we consider a new matrix that contains the matrix of coefficients? That would be this rectangle, and it also contains this vector B as an additional column. So this new matrix is what it will be called the augmented matrix. Is the matrix of coefficients augmented by an additional column. Okay, and so that's what we mean here. So we have A, we have B. The augmented matrix will be one that has m rows and n plus 1 columns. Okay, and one way of denoting that is we write A, and then we write a vertical line there, a vertical line separating the matrix and the new column B. So that would be the augmented matrix. And why is this important? This will be important because the operations we will apply will be applied to an augmented matrix. So here's an example. There are 3 equations, 3 variables. The matrix of coefficients is augmented with an additional column that stores these values on the right side of the equations. So those values are the right column appear here as the last column. This is a matrix that has 3. This is now the augmented matrix. It has 3 rows and 4 columns. So the operations to be applied to the augmented matrix are the following. They are consistent with equation operations. Remember, well, the operations are the following. There is an exchange. There could be a swapping of rows in 2 different locations of the matrix. It is allowed to multiply one row by a non-zero quantity. It's going to be called a scalar. The scalar is another word for saying a number. And then you can do the following. You can do basically number 2. That gives you a new row of numbers. But then you can take that row and add those values to the entries of another row. You do that column by column, entry by entry, and then leave the first row same after this operation, but replace the second row with the new values. Okay, so there will be some notation for this. The swapping of rows is going to make use of this double arrow. So this denotes this R here, denotes row I, and this R sub j denotes row j. And what we mean with a double arrow is swap the location of row I and row j. Alpha multiplying R sub I means that there's a scalar alpha, there's a number, non-zero quantity, that multiplies the ith row of the matrix. And then this operation means take the ith row, multiply that by a scalar alpha, that gives you a new row, and then add that to another row here denoted as R sub j, and this whole thing is going to give you a new row. And then according to this notation, what we're going to do is to replace the row that appears listed last. Okay, this is a sum of 2 things, and what appears in this sum last, that is what will be replaced. So by applying these operations, we are going to modify a matrix, and this modification will be a new matrix that is in fact row equivalent to the original matrix. So here we go. This matrix A, if we apply some of these operations, we will end up with a matrix we're calling B here, and therefore these two matrices are row equivalent. For example, look at the matrix A, look at row number 3 here, and what we're going to do is we're going to swap locations between row 3 and row 1. So by swapping locations, then the former row 1 will appear here listed as the last row, and the previous row 3 is now the new row 1. So that's what swapping, that's the idea of swapping. So you can see that this new matrix here resulted by applying one of those operations to the original matrix. Therefore, we say that B is row equivalent with A. But there is more. What happens if you take row 1, multiply row 1 by -2? Well, this would be row 1 of this current matrix. So if we multiply row 1 by -2, here we have -2, -2, 0, -12. And the current second row here is this row. So what comes next is to do the addition entry by entry. Okay, so if we add -2 plus 5, we're going to get 3, minus 2 plus 2, we're going to get 0, 0 minus 2, we're going to get -2, and -12 plus 3 is going to give us -9. So those are exactly the entries that appear on, where do they appear? Well, they appear there on the second row, because that is exactly what appears listed last, right? So when we are writing something that looks like alpha r sub I plus r sub j, then what we mean is that in this notation, we carry out with this operation, but then we also pay attention that the thing that appears last listed, that is what will be replaced. In this case, is r sub 2 that tells us we're going to replace row 2 with the new row. Okay, so we can also say that any pair of these matrices are row equivalent. So this matrix here in red is row equivalent to the previous one that has the entries in yellow or gold, and that is row equivalent to this one, and so on. If two matrices are row equivalent, and they happen to be augmented matrices corresponding to a linear system of equations, then those systems of equations are equivalent systems, meaning that they will have the same set of solutions, the same solution set.